Okay, sorry about that, guys. So, and someone asked about this in last class, and I said we would get to it, and here we are, is VHDL is weirdly particular when it comes to dealing with types, right? It is very strongly typed, and what it allows you to do with certain types is it's very picky. It has a hard time. It doesn't even let you add bit vectors, which is problematic. So we want to use libraries, which I highly encourage the use of, and this is how. Let's see. Numeric Bit all. That's an underscore. This lets us bring in the Numeric Bit Library from the IEEE main library. What this does, and is very useful for, is allow us to bring in unsigned and signed types. Those types can be as long as you need them to be, and they bring in overloaded operators, which means that your operators can do more than one thing, right? So you have to be careful and make sure that you're set up. If these were bit vectors, this would not work. If these are unsigned or signed types and you have this library, this will work just fine. This will add them together. So it's going to give you all types of operators for this, plus, minus, multiplication, remainder, etc., equalities. But we also want to step up to some more complicated stuff because we want to use bit vectors. But first, I'm going to just use a quick example of this, right? So now if I'm adding something like a sum, where I'm adding two unsigned types and a carry, right? Because I want to create a full adder. And this, if this is a bit, these would add fine, that does not add fine. So unsigned, bit cannot add those. But it does give us tools to fix that simply by writing so if I call it carry in, CI instead of just carry, I would just write unsigned, do a type conversion. So I'm converting this to an unsigned. So the type conversions that it's add is also very useful. There's an example on page 92 at the bottom of that walks you through using the unsigned conversion. And it also shows you how, because you have an issue, right? If I add these two together, and I have a 3-bit vector, what is the result? 0, right? Because these get carried out, and it's not. So this actually has a pretty decent example of how they append an extra 0 to this addition in order to not lose the carry, rather than worrying about calling it specifically a carry out. And it's got it pretty good. So you can convert with this library to integers, to unsigned, and you can also convert to bit vectors, which is all very useful. But if we really want to get in with bit vectors, we also want to use IEEE dot the standard logic library. Now, if you ever go and look on a VHDL example, almost all of them will use this library because this allows you to start using addition on bit vectors. I always use that library, and I start using the standard logic types, because then I can add them together, which is really quite helpful. So their short way of explaining it, and it's kind of funny because this is in the IEEE library, but it's not really an IEEE standard. But it's so common that they've just added to the IEEE library. There's an example of that in the book. These are the core libraries that should do for almost everything we do this semester. The next thing we need to know how to build are shift registers, right? And a shift register is you put data in one end and it comes out the other end in order. If you were going to build something like so, right, and each of these are just D flip-flops, D and Q. We all remember process from last time, I hope. And I'm just going to write rising edge. Right, there's code to do for the rising edge, but I'm just going to shorthand it. So this is just going to shift through. We're in a process, so do these happen in parallel or sequential? They're sequential, because it's a process, sequential. So it assigns Q1 to Q3 after 5 nanoseconds. What do we remember about this after 5 nanoseconds? It does not synthesize. But this is a great case where it is actually helpful to put it in, because when you simulate this, they're going to update after delta, right, which is the smallest time step that it can manage in the simulator, essentially. And it's going to look like just a cascade of data. If you add the 5 nanoseconds, it's going to simulate more like what's really going to happen. 5 nanoseconds is a reasonable amount of delay for that, and that can help your simulator look more like what reality is. And that's just something you'll grow to become familiar with. Now, you may end up wanting to do something more useful than this, because the problem here is there's no way to get data into this, right? It's just a loop around. Now, if you were trying to generate a pattern, this is actually fine. This is a really good way of doing it. But if you're trying to get it in, you may want to use something like memory storage, right? And this and it's going to be clocked. So here, I want this memory on the clock, sorry, there's an A there for some reason, clock edge. And I'm probably going to build an enable for this, right? Because I don't necessarily want to do on every clock, I just want to do it when I tell it to. Right here, and I'm just going to write this process on clock, if it's the rising edge, and I'm going to start with if clear. So if I want to clear it, I want that to be the first thing. So my first if statement in this block is going to be if clear, delete the memory, right? Because I don't necessarily want to always remember it is. I want the option to get rid of it. Then else enable, another term that they'll use for it is load. So if load and clock, then Q equals D. And if you remember, with bit vectors, I can really just write that, as long as these are all defined as 4-bit bit vectors, right? That will assign all 4 Qs to all 4 Ds in order. And then you're done. You have a nice little block of memory. There's also an example of a left shift register in here that I won't go through just to keep it going, that shows you how to bring in new data and step through. And you can write it 2 different ways, right? You could have essentially this guy as a shift register, and instead of just, we'll call it load for now. So instead of just load, I would also have shift. And the 2 things that I could do is either load all of that data in parallel or shift it out one at a time, right? And that can be very useful in something like serial communication, where you have a big vector that you want to load in to be ready to be transmitted, and then transmit it out 1 bit at a time. That make sense, everyone? You can really easily, and you will do this all the time, create counters. They have a lot of different ways to create counters in this book. I'll just do one here. Sorry, this notation is wrong. I'm used to Verilog, so if I'm doing these parentheses on the ifs, that's why. VHDL doesn't actually use the parentheses, and I keep forgetting that. Right? If clear, go to 0. Else if enabled, start counting. This type of design is clock gated. So you'll notice the process executes every clock, but then only counts if enabled. So the clock enable architecture is really useful. Try and design your counters this way. Don't just say each clock count, do clock and enable. I'm not going to dive into it right now. We'll probably get into that later of why that's true. But that if you just count on every clock, you can end up with an issue of, it really comes down to a timing issue. And so you may want to count every time some event happens. That event might be happening at 10 kilohertz, and your clock is 100 megahertz. When you do that, run the process at 100 megahertz, and then put the enable signal on whatever event you're trying to count.
What is the RE?
Rising edge. That's just my shorthand, so I don't have to write out the whole code.
Can you write it out once, please?
Yeah, so there are 2 different ways to do it. If clock event, this tick event here, is just intrinsic to VHDL, that is just watching clock. And if an event happens on clock, and that clock is 1, that'll give you rising edge. Similarly, you could do if clock event and clock is 0, that'll give you falling edge. You can also do, and I'm always a little off on this, but I believe it's just like so. If you just do if rising edge of clock, that has its own way of detecting it. This might be a little bit off, but it's similar to that. On page 98, there's a fully synchronous counter that is just all the Verilog code. It's a very robust counter that is a good example to look at if you need a big counter ever that has clears and loads and all that. As I said, there's like 5 different examples of different types of counters in this book. So at this point, just like to review this idea of abstraction, right? Just to reinforce it, where as designers, you may be drawing blocks like this, right? Where we know there's logic in this flip-flop, but we just draw the block and we have symbols in it that let us know what it is, right? That's highly abstracted. We could also do something right and draw a gate level design for this, which is less abstracted. You could even, if you're really into it, go and draw the same circuit at the transistor level, right, where your flip-flops are all going to have some sort of circuit architecture in them, right? And we could build that whole circuit in that. And you could even go further than this and actually start drawing this out in a layout tool, which is not abstracted, right? So there is a connection between this and the physical layout that ends up on your ASIC or in your FPGA. But we call it abstraction when we start drawing these diagrams. But now we're going to move on to what is really, by my estimation, the most important part of VHDL, which is state machines. Now, my night class apparently has some trauma remaining from the state machine section of their 2700. I really like state machines, right? You get to draw them as just circles, right? And if I'm in some state, I know that I'm either staying in that state or going to another state. And I might have other transitions. I might have other options to step between states, right? I don't have to always go from 1 to 2. And it might go 1 to 3. But once you can start drawing the state machine, it's really easy to start thinking about these state machines as VHDL code. Now, there's 2 ways to design this, really. You can either throw all of the state machine into one process or into 2 processes. I tend to use the 2-process method, where I have one process that is doing something like this. And I'm going to point out the shorthanding. Normally I'd write end if and end process, but I always shorthand that just while I'm writing on the board. So all this is doing is every clock, the state is taking the next state, right? But the next state might be the same state, right? So that guy is always just kind of ticking away, doing what it needs to do. Then I'm going to have some more complicated state or process that does, I'll use the case example because that's what I like. We're going to case on state, right? Because what we want to do is based on state. And then you just say is, if you recall. Sorry, this should be so. So I'm going to have another process. I'm going to case on state is when I'm in state 0, then my z, my output, is 1, and my next state is going to be 1. So this is saying at case 0, always step to the next state, right? But you can see how you would potentially do something like when 1, then define your output, and then you could add some more logic. And just instead of saying next state is 1, you could have some next state is equal to A and B as the inputs, right? And depending what those inputs are, changes the next state. Or you could build up even more complicated logic that is like a traffic light, that if a pedestrian has pushed the button, then go to the next state 3, or whatever it happens to be, right? This is an example of a Mealy state machine, right? Where Z is defined within the when, but you can do more state machines more easily, in fact, is my estimation, where your output is defined within the state. This will walk you through a whole state machine on it, but just remember, have something, the easy way of doing it, have a process that's always updating the state based on whatever next state is, and then have another process that is the logic within those states for making those decisions. And you can have the whole state machine within the case statement. And you will do exactly that in Lab 1, probably. Yeah.
Is the Lab 1 pure VHDL or also?
No, Lab 1, we're going to write some VHDL, we're going to simulate it, and then we're going to throw it onto the FPGA. And I will actually go through what we're doing for Lab 1 in class today. I have posted an updated lab description online, but I'm still going to walk through it so that you have a clear picture of it. On page 106, they give you an example of how you do that all within one process rather than use a monitoring process and a state process. And then tons and tons of examples. This book does a really good job of examples. But I need to get to arrays, right? Arrays are important when dealing with large data sets or when doing something like image processing, right? Image processing is naturally multidimensional, and FPGAs are getting used more and more in image processing applications like computer vision and such. So if you wanted to set up an array, you could do something like, let's see, what's the right one to do? I'm going to create a type. I'm going to call it a matrix, and it's going to be matrix 4x3. And I'm going to say it is an array. Sorry, I have to erase this. And then to let it know how big it is, it's 1, 2, 4, and 1, 2, 3. And its type is integer. Now, when you create this, you can create an initialization. So I'm saying I have a variable. I'm calling it matrix A. Its type is a 4x3 matrix, and this is what it's initializing to. What that will give you is this 4x3 matrix. and you can go pick out a matrix element, just like you would in MATLAB. Right, where you'd go, I want element 3, 2, 3, 2. Right, and that's how it accesses individual elements of that array. Excellent. Cool. Do we have any questions so far on the VHDL?
Sorry, I didn't notice. Is this a zero basis? So 0, 1, 2, 3, 0, 1, 2, or?
So VHDL is almost always zero based. The matrix, for some reason, is not. I don't know why.
Did you do 0 to 3 instead?
I don't know. I haven't actually designed anything with a matrix yet in VHDL. So as I said, I've done everything in Verilog. Verilog, you can do it at 0. This, maybe, I don't know. I don't have an answer for you. I'm sorry.
Okay. And then none of the operators are case sensitive, are they?
Nothing is case sensitive, no. And none of the operators, and in weird ways too. So at least in Vivado, the old edition, if I do process versus process, no difference. So even process is not case sensitive. Yeah.
Are the names of variables or like?
I haven't tried with the variables yet. I haven't checked that.
I've been loose with my capitalization and variables. It should work. It's not, I don't think it's case sensitive.
Okay, yeah, that's good to know. Yeah, I tend to be very consistent with my variable naming, where I tend to start with a lowercase variable, and then if I have another thing, this is kind of bad, I alternate between using the underscore variable a, right, or if I was doing like add, sometimes I'll do the variable capital add. But those are the only two formats that I really use. And as with all of your other programming classes, we highly recommend using very descriptive variables, right? Don't just A is not helpful. And you can declare constants in there. I think we covered that. Did we cover that last time, the constants? If not, it's in the book where you can declare constants, so you could define a constant, say delay. And you're going to say, I'm working with a lot of flip-flops, I'm going to guess or I'm going to have the same delay. So I'm going to create constant delay, and then every time you do it, instead of having to write what the delay is, just write delay. And it carries through. But what we're going to do now is we're going to move on to the description of the lab, because I really want to get this started. So initially Lab 1 was scheduled for next week, but we had no real hiccups in Lab 0. So I feel like moving Lab 1 up into now is a good idea in case we end up going online due to COVID. So there is, and we may only get through half of it since effectively we're all new to VHDL, right? So the good news is with an experienced designer, what I did, I built it in Verilog in about 3 minutes, the Lab 0. I still have some bugs working out with the VHDL version of it, but it's not that complicated. So what we're going to build is a serial receiver. So what serial means is it's all coming in line. It's not parallel, right? And it's what we call UART. Now this is a very old school style of communication where you're going to have 2 dedicated lines, and this will be on the PC, and then over here we'll put our FPGA. And they're going to be wired together with 2 lines. Again, it's digital, so it could only be high level or low level logic. So what we're building is the receiver. Now, it's kind of interesting that the labs are laid out this way because the transmitter is actually easier. But we're going to start with the receiver. So the PC is going to send data. This is what we call asynchronous, meaning there's no clock to it. So it needs to have an idea of when data is coming and what it's doing. The way this works is the line sits high to let it know it's active and plugged in. When it wants to start communicating, it has what we call a start bit, where it drops low for 1 bit cycle. And that says, I'm about to send you data. Then it sends a block of data. Of 8 bits. So this is the UART standard. Start bit, data bits, stop bit. There is an optional something we call a parity bit. And the idea of the parity bits was from a time when UART channels were really bad and we were not very good at this stuff yet. We wanted a way of checking the data integrity. And the simplest way of doing that was to have a parity bit that would basically count up the number of ones in the transmission. And if it was odd, it would send a 1, and if it was even, the parity bit would be 0. And then if the number of ones didn't match the parity bit, then we go, oh, there was something wrong, please send the data again. Now that's obviously problematic because if you lost 2 ones, nothing changes and it looks okay. But they assume that the probability of losing 2 bits is much lower than just losing 1. Yeah.
What do you mean by losing 2 ones?
So if I had a signal that was supposed to be zero, 1, 0, 1, 0, 1, 0, 1, right? I would have 1, 2, 3, 4 ones. And therefore the parity bit would be 0 because I have an even number of ones. Now it's possible that the transmission line is really bad and I never get up to that value. So my actual waveform looks more like that. And these both get counted as zeros. My parity bit is still 0 because I'm still even, but I got the wrong numbers.
So check is if it's even.
Yeah, just checking if it's even or odd. That's the very simplest parity bit. There's a much more complex one where they use multiple parity bits, but that's what 1-bit parity does. But generally, we don't lose more than 1 bit in a transmission, unless you have a really bad line, in which case parity isn't enough, right? Because your data transmission rate is so bad anyways that you need to just slow the thing down and not lose as much data. UART, like this, is fairly limited. You have some pretty common bit rates. If you look at like Arduino examples, they almost always start with 9600. We call this baud, the baud rate, but it's really just bit rate. And so 9600 is really common, but it's very slow. Other common numbers, like 15200. This is one that I use all the time because it's fast enough for most data, but it's not fast enough to cause problems. You can also go up to like a megahertz. The fastest I've ever gotten just UART to run is about 1.4 megahertz. I haven't had much luck past that because it doesn't have a clock to tell you when to do it. So the way this really works is you're just counting, right? This drops low. You wait half a clock period, and you take a sample right there. And then you wait 1 whole clock period, again, and again, and again, and you sample, 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 right? And that will give you all of your bits. What tool do we have that could implement this type of repeated measurement that we've taught? A loop, close. And a flip-flop is in the right direction, but it's just a state machine, right? So I have state 0 that is really waiting, right? And it's just saying if high, chill here. If low, now there's a couple different ways to do this, and I'm not going to give you all the answers to this because part of the lab is going to be puzzling through. One of the ways, right, is I've detected low, I have to wait the right amount of time. This second state could just be tied back and set on some sort of counter, right, that is just waiting the right amount of time. And then it's after that counter is done, it's going to go to the next state. And that next state can be done a couple of different ways, right? You could do it the hard way, where you have one state for every single bit. Don't do it that way. State 2 is perfectly capable of just repeating itself while shifting out data, right? So it's actually going to be 7 times because you can store the first bit here. So then 7 times is just going to loop through here, again, just a counter. And this is going to have an output where I guess your book is going to draw it like this, where the output Z is equal to whatever the data is. And that's all just going to load into a shift register, right? And so that's going to slowly fill up. You have some shift register, that data is going to pour in, load it up. You're going to get to the stop bit. During the stop bit, this guy's going to be full. You can use that opportunity to transfer all of this into some memory to hold on to it while the next process starts loading, while the next bit starts loading. Yeah?
And we're just doing 8 bits.
Just 8 bits.
So is that how it knows when it's done?
Exactly, yeah. You have to define how many bits it sends at a time. We call another term for that the start bit, stop bit, and optional parity bit. We're not going to do parity, but start bit, stop bit, and optional parity are all what we call overhead, right? Because I have to send 3, well in this case 2 bits extra for every 8 bits that I send. So if you end up needing a lot of data, high speed on this, then you might have this data load could be a kilobit, right? It could be a ton. It might be kilobyte. It might be a megabyte. Not really. You don't really that big, but you could have really large packets. That's what this is. That's a packet.
So start bit is 0, end bit is 9. Technically, right?
Say that again.
Start bit is 0, end bit is 9.
Yes.
And then 8 bits in between is the actual.
Yeah. Yeah. So I need 10 bits per packet. And so, having done designs like this, when I hand it off to someone, I have a packet definition. Because a lot of times you'll actually have a much larger packet that will have like a command in the beginning. So it'll have a start bit, a command, data, and then some sort of verification, which is more complex than just a single bit parity. So you can build up fairly complicated packets, but this is the simplest one. So the clock on both ends then, it has to know, both ends have to be told what the baud rate is, because they have no mechanism for telling that. With the PC, you may have heard of applications like Putty or Termite. So Putty is super popular. Termite is my favorite because it's super simple. It's the most like straightforward, just get up and running. And what it does is it just sends over USB. It uses USB like a serial port with 2 wires. That's what we're going to be doing. We're going to be plugging in a USB cable into your FPGA, which does anyone have it with them? Just one wants to get it out. I mean, cool. So the nice thing about this FPGA, and one of the things that sold it on to me, is we've all plugged this in before, right? So your power goes in here and plugs into the PC. That same USB cable has a second device on it. So USB can have multiple devices. The second device is a COM port. And so using that same USB, you can send serial data back and forth between the PC and the FPGA. So you need one cable for the communication. It's very nice, very useful. I have some complaints with the way they wired it up. They didn't do it as good as they could have, but it should still work probably even twice or 3 times as fast as that, if you wanted. I've kind of written the lab assuming 9600 baud, but you can increase that if you want. So what you're going to do is, part of the lab is writing up a diagram of what this looks like. That part that the USB plugs into goes from the USB to this part called the FT2232H, and then into the FPGA. Now, part of the description is asking for pin numbers. I only care about the pin numbers on the FPGA. You don't have to go and look up what pin numbers the USB is plugged in onto the FT. The reason I want you to look up the FPGA is because you need to figure out how to tell the compiler to connect that in the FPGA, right? Because you're going to have some TX and RX line. You need to tell them how to connect up to that hardware. So for example, if you look at the code that we used for Lab 0, it has that 100 megahertz clock, right? That's the signal they use for your clock. And then if you go and look in the .xdc, the constraints file, they link that to W5. The reason is W5 is your dedicated 100 megahertz clock pin. You're going to have some dedicated pins that are connected to the FT part. You need to look up what those are. So you're going to use, the steps of this are, number 1, you're going to write a state machine You're going to write a state machine that is a receiver. Then you're going to write what we call a test bench, which is designed to test your code. So you will test just the receiver, right? You're going to treat it like I'm sending it data bits, and you're going to see if you get the data bits. I will show you how, either in here or in the lab, one of the two, kind of how to write a test bench. They're really not very difficult, which is very fortunate. But you're just going to simulate signals going into it, and your state machine is going to pull data from it and load it into some buffer, which you can then do something with it. The something that we're going to do with it is you have those 4 7-segment LEDs, right, that can make any number on them, letter or number, right? What we're going to do, because I don't want to make this too complicated, we're going to use that code. That code currently controls those LEDs using a counter. So after you've simulated the receiver, you're going to pull out the counter, and you're going to put in the receiver in its place that is going to load into memory some sequence of 8 bits. And then you're going to send those bits 4x4 to these 7-segment displays to verify that it's working. So say that this is, I actually don't know, but it's something like a Y. This 8-bit is an ASCII code. We're not going to display the Y on here. We're going to display whatever code is already used to that. So there's going to be some decoding in here to make sure that the bits that we send match up on the LED. Yeah?
So it's not hex. It's not going to display as hex.
Well, the display is hex. right? But there's an encoder in here, already built in Lab 0, that you don't have to worry about, that turns 4 bits into some sort of display. So you're just going to accept their encoding scheme and just have to kind of do the translation. So I'm going to know what a Y is and what that should display. So it's going to be as simple as me walking by and pushing Y and sending it to your FPGA and seeing if I get the right, which it might be like 2 and 1. It's not, right, because we could figure out what that is, because these are hex. But this is not. We're going character to those. Shoot, there was something else I needed to say that I've lost track of. Give me a second. Do you recall last lecture when I talked about components? That's what we're going to have to do. We're going to create a component to replace the process that is currently a counter. So you're going to replace the counter process with a component that outputs to a memory block that updates these. That's the lab. If all we get done this week is through simulation, because I'm not sure if they've gotten my serial programs put on that lab yet, I'm happy. If all we do is simulate, I'm happy. Because as I said, the receiver is more complicated than the transmitter. So if we get the simulation done, then next week I think we could actually finish 1 and do 2. And the lectures are actually pretty light for next week. Any questions? Nothing yet. Yeah, that's the catch. Let me flip through this so I can remind myself on the.
I guess just to make sure I'm understanding everything correct, we're gonna like push a button on the keyboard on our computer. It's gonna send it over using like Parity or Termite or whatever.
Yep.
And then the FPGA is gonna receive it, and then we're gonna display out the like hexadecimal representation of the ASCII number.
Yes, exactly. That is a perfect description of what we're doing. We've got 15 minutes left. I'll just call it a little bit early today. Spend those 15 minutes, if you don't mind, just go look up just some example test benches. I will cover those in the lab. I'll get something nice prepped to show you guys. I didn't expect to finish this early, but I will get a test bench prepped to show you guys how we're going to set that up. But most of the work will be programming up the VHDL state machine and making sure that it works. And the simulation is make sure it works. Yeah.
I actually just had a question on the schematic.
Okay.
From the lab. So is that all you're looking for right now?
No, that's actually pretty close, actually, to what I'm looking for.
Because it mentioned also a ST3232, which is, in my mind, a voltage converter for the FPGA. I would assume that's what it is.
Shoot, did I not delete that out?
No. I'm
Okay.
assuming we're not using that.
We are not using that anymore.
Okay.
So I have 2 different ways of doing it. We're not going to do that right now. We may end up doing something similar to that for the final project when we bring it all together.
Okay.
Because this is actually kind of interesting. What this is building into, the system, is a little bit in flux at the moment.
Okay.
So the labs, as they're designed right now, we're just building up a dummy terminal, which is where you're going to be able to plug your FPGA into a monitor and a keyboard and program it up that way. And you'll be able to type it in. It's just basically building a typewriter. But that's not that interesting to me, so I'm working on revamping the labs. I have to stay ahead, and it's a busy semester for me, being it's my first semester. But I am trying to get a better project out of it.
That's good.
So hopefully you're all willing to go through some learning pain with me to do that. But you had a question? I thought I saw a hand over here somewhere. Okay. Okay. Yeah, so I would like to get a point where we're using an ADC, actually, and we're bringing in signals that we're recording and then transmitting those to the PC.
Nobody has any questions?
Yeah.
We're mine. They have a solar simulator that's supposed to represent the sun for testing solar cells. Problem is right now, it's a halogen bulb. It's sitting on a stand. It's not an accurate representation of the sun.
Right.
They can't publish it. And it's also incredibly hot, and it's also incredibly bright because it's poorly built. So like if you turn it on, it radiates this way. So they want basically a variable light output spectrum so that they can match like the stars, or they can go red. And so basically just whatever that is will be right then, and that display
The A, B, not.
controls read those, but I can incorporate microphone.
Okay, so just
That'll give me the ability to save values, so if they're constantly using them, they can save it in. Reload the data at any point, like, hey, we're going to be looking at this for a while, so let's rewrite this default value to this.
I'm looking everywhere on my board. I don't even know what this is.
This might actually update.
Yeah.
Instead of just
Looking
fixed
everywhere,
light
like-
that they can never update.
That's
Right.
So it's falling the line.
So that's what,
Like that's the
hoping.
Yeah, that's good.
Okay.
Next into the FT right there. Got that on the board. This
I
is
see your
something
project.
that
It's
is
actually
like did that.
I don't have any contacts yet. Still trying to get with these. And I've worked with Dr. Rapinski. They shoot classes, kind of like a mix of 4 of our classes for them. It's like circuit analysis, looking at my embedded, jammed into one semester, and I had that with them too. And so I've worked with them. I got a lot more than 4A. Yeah. Students are I helped at that. So I'd like to kind of do something.
Oh, that's right. You have.
Yeah.
Thank you, sir.
I redid mine like twice.
Yep.
Unsigned signs,
Yes.
I could probably do that now.
or what's the significance?
So unsigned is only positive numbers. Signed has negative numbers. So signed is stored in a 2's complement bit vector, whereas unsigned is just stored in a standard bit vector.
So unsigned can be negative.
No, unsigned means no sign, which means positive only. Yeah.
So that
Yeah, and so the way to think about it in simple terms is if I have a 4-bit number, is this a sign or not? It depends. So in a sign, this is the sign.
I can do it that way.
In unsigned, this is part of the number.
okay, gotcha. And
So-
the one being negative. Right?
Yeah, so this is either -1, sorry, it's either -0, which is really kind of a funny thing to do, right? It's -0. Or,
It's a 14.
well,
Or positive.
positive.
And then I have
And then it connects to the HDA, and then I have 2 pins for this.
I got E not there.
Also, it's good for the.
So it's like either two's complement.
Yeah, so this is not really 2's complement, but that's the idea. So 2's complement, this, rather than just being a sign, has a magnitude.
And the advantage is
There is no, obviously there's no.
Yeah,
You know-
it means that I don't have a -0 and lose a bit. It's a minor improvement.
And then they get shifted over.
And if I know I'm only going to work
So-
like the last
Then you'll just use unsigned,
It's supposed
which
to
is
be-
very common to use only positive numbers.
So it shows
But no
one
more.
here and then one in the other.
Thank you so much.
Yeah.
Yes.
And then I'm guessing.
You got a stapler in here? No.
Not that I
I'm
know of.
assuming so.
Are you taking homework now or?
I mean, that's.
All submissions online. Will we do it online? Yeah.
That's based off your signature. Well, how you want to choose to shift it.
I would see this one after.
You just want PDF. submitted to
Yep.
Canvas.
Or just
Exactly.
when you shift it,
Okay.
then we shift the other one over.
This is one time.